Hello everyone, my name is Circadian and I'm one of the authors of the paper titled Towards Classifying Human Circadian Rhythm Using Multiple Modalities. In this presentation, I would like to discuss certain key points in our paper. So I will start my presentation with motivation and the objectives we set out to achieve. Then I will describe the data set used in detecting circadian rhythm. Later on, I will discuss our methodology. Finally, I will present and discuss our experimental results and conclude. Starting with the motivation. So circadian rhythm refers to biological variation of rhythms with cycle of approximately 24 hours that will persist even when the organism is placed in an environment devoid of time cues. So by understanding it, it will be possible to cater to the needs of the travelers by adjusting lighting, audio, and temperature settings to maximize their rest over long trips. So moving on to objectives. So in order to detect circadian rhythm, we set three main objectives. First of all, collect novel multimodal dataset of 36 subjects. Secondly, we aim to improve the performance of circadian rhythm detection by integration of multimodal features such as visual, thermal, physiological, linguistic, and background data. Finally, our research is an attempt to model circadian rhythm using a multitude of data channels and a non-invasive approach. So for our dataset, this table summarizes our dataset that we gathered from the 36 subjects of varying ethnicity, with each subject undergoing 5 recordings in a tobacco, alcohol, and drug-free state to detect their circadian rhythm. So using these recordings, we were able to extract 120 thermal features, 709 visual features, 71 physiological statistical features, along with 58 linguistic features. So in order to extract these features, we followed certain techniques. For the 58 linguistic features, we extracted it using NLTK and TextBlob libraries, while the physiological modality, the 71 features represent statistical measurement derived from the raw signal. To extract the thermal features, we followed three main steps. So we started by segmenting the subject frame into 5 different regions. Afterwards, we tracked these regions throughout the recording. Finally, we created the thermal map that represented the thermal distribution in the region of interest following these steps of region of interest segmentation, segment binarization, image masking, and finally thermal map probing for each region of interest. This process is illustrated in this figure. So for the visual features, we use OpenFace library to extract facial landmark position and head pose, eye gaze, and the presence and intensity values of action units such as blinking. So this figure shows estimates of the gaze and head pose, as well as facial landmark detection for a video frame from our dataset. So the pink lines denote the estimated eye gaze vectors, where the 3D representation indicates the head pose estimation. Looking at classification labels, we used the Karolinska Sleepiness Scale KSS survey. So in addition to the time hypothesis to label our data. So KSS provides a score in the range of 1 to 9, where 1 indicates that the subject was most energized and 9 indicates the greatest innervation. Using the KSS survey, we were able to model this range into binary and trinary problem as seen in this figure. So the classification was carried out using 2 approaches, unimodal classification and multimodal fusion, where we used early fusion, late fusion, and metafusion. The latest fusion, which is metafusion, is shown in this figure, where a new set of distinct fusions were generated from the distinct individual modalities, and by using majority voting on their decision, final predictions were generated. So moving on to our results, this figure presents the performance of each modality in 5 classification tasks, where the thermal modality has the best performance of approximately 65% accuracy with the morning-evening time labels. However, for the KSS labels, the visual modality is the best performer with approximately 61% accuracy. Here, we demonstrate the results from early and late fusion, with early fusion reaching about 71% under the time label. For the meta-fusion, it achieves the best performance compared to previous results with 77% accuracy and 79% as a recall. In this graph, we explore the coherence of subject self-reported chronotype, which is in orange, along with a SAS chronotype in blue. It shows a higher coherence for subjects who self-report as evening types. A possible interpretation is that the subject who self-report as morning types may not be fully aware of their own chronotypes. This chart similarly shows the coherence between self-reported chronotypes on the right and morning eveningness questionnaire on the left, which results chronotype based on the results of a questionnaire. Again, we can see the greatest overlap in subjects who self-report as evening types. Finally, these two charts show the correlation between certain features and an innervated state as a negative value or an energetic state as a positive value. Chart A shows that higher temperatures were recorded in the face while subjects were innervated, while chart B shows that certain features, particularly blinking, were correlated with innervation. So to conclude, we introduced a novel multimodal dataset for circadian rhythm detection. We found that the thermal features provided the best indication of the circadian state compared to the other individual modalities. Also, we developed a multimodal circadian rhythm system that aids in the detection of the occupant's state. And finally, based on our analysis, we have found incoherence between certain subjects' professional chronotype and their result chronotype. Thank you for your attention, and please email me if you have any question regarding the paper or the presentation.